once you understand the meaning of stress transformation, you should be able to calculate a normal and shear stress on any plane. Do not just remember how to draw a Mohr circle. You have to understand what it means, what the stress transformation means. That's the most important. And again, the stress transformation means that we have a body like that, and we are given a stress at this point. Okay, we have a stress here, and sigma xx and xy and xz, and those 3x3 component stress are given at that point. Okay, simply the coordinate is like that. So whenever we describe a stress state at a certain point, you will notice that we have to have a coordinate together. If we don't have a coordinator, we just say this one, it doesn't make sense. Because each stress component will mean that, okay, sigma xx means that we just cut through an x-plane, making x-plane, and then there will be a three force. And these three force will mean this, right? What this, it doesn't matter because shear stress are symmetric. 이해했죠? 네? So anyhow, to do that, as you can see, this we need to have x and y and z coordinate system all the time. So now, the stress transformation means that we are given a stress here. We just express a stress using this coordinate. What if we have a certain plane which has a certain angle with respect to this xyz coordinate? And the question is, what kind of a distribute load will appear on this surface? That's the question. And that's what stress transformation means. Okay? Let me ask, if this plane happen to be a vertical, happen to be this axis, then what kind of distribute forces will appear? This, right? Simply. Again, the question is, we have a n vector, and simply which has a certain angle with respect to this theta, let's say theta here, and there will be some kind of distributed load. Resultant will be like that, and this one will have a certain component, this and that. So if we say this is the n vector, and this will be sigma nn, and sigma this will be nt, right? Yes. So again, if we refer to one-dimensional case again, this is a sigma xx. So inside the body, we're subject to a sigma nn, meaning every cutting sections will have a sigma nn like xx like that, right? And question is that what if we have a certain plane? We have this kind of cutting plane, and what kind of stress component we will have on this plane, which has a certain angle with this x. So this will be theta, and that is the sigma nn, and this will be the sigma nt, right? We reviewed that one-dimensional case many times, and in terms of a Mohr circle, it's simply like that, right? So this is the, if this is a sigma 0, this will be sigma 0. And as you can see, the shear stress will reach maximum at 45, 2 times of 45, this is 90, right? That maximum, the value will be half of this sigma 0, right? And this one, this is a shear and normal component. So normal component and shear component will be half of this one. And as you can see, this is the above, upper region. So a shear will be negative. That's why we will have this direction. Okay, anyhow, so let's say the question is, if you have a problem, as she said, the question is calculate normal stress in a plane with a certain angle. If the question is like that, you calculate this sigma nn, which appears on this plane. How do we do that? It's exactly the same as that procedure. You draw the Mohr circle and you rotate 2 theta in the Mohr circle and you get the normal stress and shear stress. You must wonder, what if we have a 3x3 three-dimensional state? This Mohr circle is only for 1D or 2D, right? What if we have a 3x3 three-dimensional component? How do we transform stress? Well, if we cut, body here, we cut arbitrarily with some three-dimensional space. How can we calculate the normal stress and shear stress? Can anybody answer? Yeah, 3 Mohr circle. That could be one answer, but nobody does that. So the answer is if there is n vector here, okay, n vector here, and we call this one is a t vector, then t vector is simply this sigma 3x3 matrix times n vector. That's it. That's how you get we call traction vector. Well, this looks quite new to you, but it is really good to know. For instance, if this one, let's back to here, this stress state is 1, 0, 0, 0, 0, 0, 0, 0, 0, right? And 45 directions, 45 is this vector. Actually, this needs to be a unit vector. N is the unit vector. N is the unit normal vector. So here, normal vector is, this is what? 1 over root 2, 1 over root 2, and 0. Right? That will be a traction vector, Tx, Ty, and Tz. And Tx will be what? One over root 2, right? And Ty will be 1 over root 2. Sorry, 0, right? sigma is sigma 0, 0, 0, 0, 0, 0, 0, 0, 0. That is this stress state, and normal vector will be given 1 over root 2 and 1 over root 2 and 0. And so traction vector means the whatever vector appear in this cross section will be what? If you cross sigma and n, what will you have? You will simply have 1 over root 2 and sigma 0, 0, 0. Am I right? Which means we draw in this way, we have, this is very important, and which we already covered, but I just explain in the other way, using some mathematical equation here. And here, even though we have a cutting plane, the resultant should be in this way. Am I right? The resultant force on this surface cannot have certain angle because of equilibrium. We only have x directional force here, and so at this plane we only have this x directional force. Am I right? Yes. That is this one. But see, the magnitude has been reduced. Has been reduced by 1 over root 2. Why is that? Why this magnitude? Magnitude originally it was a sigma 0. If we have a cutting plane like that, the magnitude should be sigma 0, but now we have a different plane and direction is still same because of equilibrium, but the magnitude has been reduced, right? Why? Yes, cross-sectional area has increased, right? This area has increased by root 2 times. If this is the A, then this area will be root 2 times A. So simply we multiply sigma root 2 times sigma root 2A will be same as this sigma 0 times A. Force equilibrium. Am I right? Okay. That is the traction. Now, okay, this is the traction, and now we have the magnitude. Now, stress transformation means we don't end here. We need to go one step further. What is that? This traction needs to be decomposed in normal and parallel. Right? So we need to decompose this one as a normal and this way. So sigma nn will be this traction magnitude divided by root 2, right? Vector decompositions. Normal component and shear component. And sigma nt will be again t, not t. I would say this is a T0. Okay, this is magnitude. T0 and T0. So simply, this is a T0. So divide by root 2, which is sigma 0 by half. And this will be sigma 0 by half. That is the same as the Mohr circle here. This is the sigma 0, and this is the sigma 0 and sigma 0. Shear stress will be sigma, half, and normal stress will be sigma 0. Half, right? Okay? So it is good to know, really good to know, T traction traction is whatever distributed load will appear in cross-section, and which is simply sigma times, this is a matrix and vector product, and times n. What is n? N is the unit normal vector to that surface. So this way is now if we use this formula, we can easily apply to three-dimensional case. Okay, three-dimensional case. If we know that traction T here, how do you calculate normal component of this vector? If you know this, a traction vector, and if we want to have a component in normal direction, how do you calculate that? Well, it's simply, if this is the n vector, it's a normal vector, then simply t dot n, right? That will be this component. So this is the what? This is the normal stress, always. And how do you calculate the shear stress? Since we know the traction vector minus this dot sigma n, and this will be shear vector, right? Simply a vector transform. I mean vector component. Okay, you guys feel very dizzy here, huh? Anyhow, it's good to know if some of you want to study further, this is a really good equations. And again, this is the shear stress, and this is the normal stress, and you can apply this equation to a three-dimensional stress state. You can certainly try on your two-dimensional case and make sure you got the same result as a Mohr circle. Okay, anyhow, that's one thing. Any other question? Yes, they are all vector. You know, this one, this is a 3x3 matrix times a vector, give us, this is a vector. And this is a vector, this is a vector, and this is a vector. Magnitude of this traction T is the magnitude of traction, but the stress, we always, stress is the normal and shear component, right? This normal term, that is this one. T vector dot n will give us the normal stress, normal component. Okay? Okay. Let us do some other case here. Okay. You know, yesterday, this is one of the simplest case, the shear case. This is the stress equal what? Zero. I'm sorry. This is tau 0, 0, 0, 0, 0, 0. That is the simply this shear stress state. Am I right? Okay, this is tau. Now, what kind of stress component we will have in 45 direction? Let's try to calculate it using that formula. And in 45 direction, let's call it this is the n vector. How do we calculate that? The traction on that vector. First of all, what is the n in component? 1 over root 2 and 1 over root 2 and 0, right? Or you can say, let's say if we, as a theta there, this will be simply cosine theta, sine theta, and 0. So this one will be cosine theta and sine theta and 0 here. And this will be what? This will be tau sine theta and tau cosine theta and 0. Right? Now let's try to calculate the magnitude of this direction. How do we do that? N dot T vector N dot N, right? This will be the normal stress. And this one will be what? This and this one dot. And tau sine square plus tau cosine square. Am I right? No, sorry, this is the cosine theta. Right, this is the tau cosine. This is cosine, and this is a sine. So sine theta, cosine theta, and twice. That is the normal stress. And in 45 direction, theta equal 45, then this will be simply root 2, and which will be tau, and which is this magnitude. No, there is something wrong here. Is it tau? Oh. Yeah, sorry. Yeah, it is tau, yes. Tau, we are studying here. And 45 direction, and we have tau here. Yes, obviously. Okay. Anyhow, this is the way we calculate, and should be applicable to a three-dimensional case. If you some of you are interested in applying this equation to three-dimensional, please try and report to me anybody who have some result. It's not required, but I love to hear from you who has more interest in these derivations. This way, you will be able to get that equation, cosine square and sine square, 2 times cosine sine theta, and all those complicated equations can be easily derived using this equation. Okay. Well, that was for the little bit about review of stress transformation. And again, I want to emphasize that as a continuation of last class, you have to understand the material properties relating stress, strain, and temperature. And especially there is a certain geometric constraint in x direction or y direction, whatever directions. If we have a geometric constraint, meaning you have strain, constraint on strain, right? Strain. If it's a free, there's a stress will be 0. If a constraint, then strain will be 0. So for instance, let's say we have certain constraint and we have a material inside. But this one has some lubricant such that it can freely extend in y directions. But x direction you have a constraint, right? Now you have certain delta t here increase, and you should be able to calculate how much stress will be developed. And here, rather than plain stress problem, this is, let's say, you can have a epsilon z equals 0, which is a plain strain. Oops. Plain strain condition. You can have either plain stress or plain strain, depending on plain strain case. You have a epsilon z equals 0. Plain stress, you have a sigma z 0. Actually, additionally, you need to have a zx, a zy, and sigma zy, sigma zx is a 0. So anyhow, whether it's a epsilon z equals 0 or sigma z 0, the stress will be different. Again, epsilon z equals 0, meaning this way is a constraint, no movement. But sigma z 0, this is a freely extend, right? So sigma z will be 0. By epsilon z, again, there's a constraint, and I'm sure there will be sigma z will be developed, right? So anyhow, this kind of problem, material properties, stress, strain, and temperature relations is really important in design of real structures and components. And you should fully understand the meaning of a Poisson's ratio. What does it mean, Poisson's ratio? And definition of stress and stress transformation, and most important thing is that failure criteria. Okay, failure criteria. Okay, well, I'm not gonna continue if you do not have any questions.
교수님 질문. 저번 주 레포트에서 5번 문제가 시계 방향으로 40도를 돌렸을 때 그 시그마 XX랑 그런 구하는 건데 그 솔루션을 봤는데 그 잘 이해가 안 돼서 그 50 왜 코사인 2세타에다가 세타를 50으로 넣어야 되는지 잘 모르겠어요.
50도를 돌려?
40도를 시계 방향을 돌렸을 때
40도를 시계 방향으로 돌렸는데
네, 그 모어 서클 공식에 대입했을 때는 세타를 50으로 솔루션을 했었는데 그게 왜 그런지 잘 모르겠어요.
if so what you rotating 40 degree.
예.
So 40 degree will be like that. So this is the plane and this is the 40 degree rotations. Am I right?
예.
Okay. So I do not know the solutions, but the whenever you draw the Mohr circle, okay, the simply procedure is this. I mean, the question is, we need to calculate the stress in this plane, right? Which the plane rotate in clockwise, right? 시계 방향으로 clockwise 40 degree. Then here you have sigma x, sigma y, and shear, and from this you have the x and y, right? Now, if you are asked to calculate this plane, which rotate 40 degree in this is in clockwise, which is negative rotation, right? We use always right hand, and this is the positive rotation, and this is the negative rotation. So rotate 40 degree in rotate in negative directions. So 40 times 2 is 80 degree. We rotate 80 degree here. Okay, and you find this one, and this will be x prime and y prime. What does it mean? This will be xx prime, and this is xy prime, and this will be yy prime, and this x prime xy prime. Simple. Now, if this one as a if this x prime is lower than this axis, okay, lower than this axis, you got this value, then sigma xy will be positive or negative? Positive. Yes. That's all you need to do. I mean, graphically, you can tell this one is how much you rotate, right? But you may wonder, this is 80 degree, how can I calculate exactly, right? You may have some difficulties to calculate, to exactly locate this position, right? But don't worry, I'm not going to ask you this 40 degree. I always 45, 90, and some, beautiful angle, not this odd number, okay? So point here is that you would have some Mohr circle, and you rotate same direction as you rotate here, okay? Just same direction, but just rotate by twice, 2 times, and then if this point is the lower, then sigma xy is simply positive. If this x is the upper, then shear is negative.
그러면 시계 방향으로 돌면은 세타를 마이너스 값으로 집어넣으면 되나요?
No, as I said, it simply rotate the same direction as this way. You rotate this way, then rotate this way. Okay? Okay. Did you have all this? Well, her question is like we have a 2 bar in series and something like this one, and then we apply load, external load here, let's say F, and question is how much the reaction force will be developed at here and there. Yeah, this is one of really good examples, and this kind of problem will be one of midterms. And is it statically indeterminate or determinate? That's right, this is statically indeterminate. Why is that? Because we would have 2 unknowns, reaction force. Okay, what is the first step? What is first step to start to solve this question? Right, free body diagram. Free body diagram. Now, question is that, is it force is this way or that way? We do not know. Right? That is the question. Which way? Any direction is okay. You just pick. Okay? You just pick any direction. Well, oops. And say this is the R1 and R2. And now we have external force here and equilibrium. Now you have to be careful. You are free to choose the direction of these reaction forces, but once you draw this reaction force, you gotta be careful about writing down equilibrium equations. Let's say Fx equal, since you have this R1 in left hand side, this is minus R1, right? And plus R2, this will be simply 0. Right? Okay. Now, next step will be, let's take a look at this guy, left hand side. And you may have some problem. Oh, how much force will be applied this far? Right? You don't have to know. This is a little complicated here. But since you already have R1 here, whatever it is, you will have R1 here. Am I right? Okay. On the right hand side, the same thing. Since you have R2, no matter what it is, you will have R2 here. Okay, now since this figure shows you that this one, you will have extension R delta 1. I would say this is delta 1. And which is simply R1, L, L1, L2, L1, and E1 and A1. That's right. And this one also delta 2 is simply R2, L2, E2, and A2, right? Now, here, another point. Now, here is the starting point, and so delta 1 will move, and this bar will move on the right-hand side, which is delta 1. And this one, we have a constraint here, and so whatever delta we calculate here, the bar will move this way, right? So this one moves that way, that one moves this way. Is it overlap? No, it gotta be moved together, right? Move together. That means, how do I say here? Delta 1 minus delta 2. Yes, that's one thing you need to be careful. And this is the one thing you need to be careful. So point here is that, okay, let's get to the solution here. So let's put this R1 here, R2 here. Okay, so and then use this one as the delta 0. Then what is that? E1A1 delta divided by L1 minus and plus R2 is this one, so E and here we have a minus, right? So minus E2 A2 and delta and L2 equals 0. So delta will be simply F divided by E1 A1 L1 plus E2 A2 what? L2. Am I right? Okay. E gives us positive value, delta 0. Means that delta 1 will be positive. Positive meaning that R1 will be positive. So it can say, aha, R1, this direction is correct. And this delta 2, it gives minus here. So as R2 is minus, aha, your direction is that way. Right? So this reaction will be this way. So you apply force. Now you can feel how much reaction and how the reaction will be. This way and that way. Obvious, right? You have a constraint here, you push this way, and there will be reaction this way, there will be reaction this way. Now if you start the solve problem with this R1 and R2, exact same result. I'm sure if you start with R1 here, then R1 will be negative. Meaning, oh, you got the wrong directions. You just reverse the directions. Okay? Yeah, this is a very much standard question, but this is a really good example for you to understand how to solve statically indeterminate problem. Okay? And especially understanding the direction of forces, how to set the problem. This is very, let's say you have more than 2, like 3 or 4 bars, and you apply load not just one place. Here, 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 and you have a here, here. It's very difficult to guess what the reaction will be, right? But as I said, don't worry, you just start with a certain direction and just solve equilibrium. And what is that called? We call material properties, right? This is a material properties, characteristic of this bar. So equilibrium equation and material property, and what is the third one? Huh? Deformation conditions. Yes, what is the deformation condition here? This one, right? Okay. Right. When you use Van Mises criterion, you have to always consider XYZ or three components. If you have only two-dimensional stress component, in problem there is always indications of sigma 3. If it says, plane stress, or there must be some given component, given value for third direction, Z components. Okay, so you should have that. Don't forget.
아까 전에 계산기 안 써도 된다고 그러셨는데 그러면 뭐 루트 계산 같은 거는 다 되는 걸로 나오는 거예요?
Yeah, you don't need any calculator, and something like that. You don't need any calculator, right? Well, you can certainly use divide by 2 times 3. You can welcome to use a calculator if you want.
퀴즈 문제 좀 짚어줄 거야. 퀴즈 본다고 준비해 오셨다는 문제가 있잖아요. 그런 문제가 너무 없어서 그런데.
Well, you have many questions in homework and many questions in previous exam. And I already went through, these things. And previous one. These things. And these things. Huh? This kind of thing. But a little bit more complicated. Not much. Okay. Mm-hmm. Mm-hmm. No, it's just as we define plus. Always, this is a positive and plus. Yes, 180 times 2, 360. Say again?
문제는 시계 방향은 40도였는데 그 솔루션에서는 반시계 방향 50도로가 나왔다고 했어요. 그러면 세타가 180도 차이가 나서 코사인하고 사인의 부호가 바뀌거든요. 그럼 솔루션이
Just remember what I explained. As I explained, this is the, sometimes they define different angles. Depending on textbook, but as I said, the result will be same. Result will be same. But as I said here, always rotate same direction as this one. If you got this way, you rotate this way. Just remember that. But difference is that if the x prime is a lower side, then is a tau will be positive. That's all all you need to remember. But some textbook, if you this way, you rotate that way. Then this one you got below, then it's a negative. above is positive. It's just a matter of definitions. But the result will be the same. Okay. Okay, so next Thursday we will have a midterm, and I want you to devote yourself wholly, and good luck to everybody. Okay. Oh, by the way, after midterm, we're not gonna have a class for 1 week. Okay?